I welcome you all in this course on mechanical measurement systems, and today we will discuss uncertainty analysis. And we will mainly focus on uncertainty analysis, and we will solve certain numericals related with the uncertainty analysis. So far we have gone through the error in measurement, and error in measurement is always established as measured value minus true value. In most of the cases, we don't have true values. We have the values which are very close to the true value, but exact estimation of true value is difficult, right? So there is always uncertainty in error measurement, right? Now in uncertainty analysis, what we do, we estimate the magnitude of error. Suppose we are measuring voltage with the help of a voltmeter, and the voltage is, let us say, 100 volts, and there is an error in the measurement of, let us say, of 2%. When we say uncertainty in the measurement is 0 to 2%, it means error in the measurement may lie in this range, right? It cannot be exactly 2%, it may lie in this range. So the uncertainty analysis, it assigns the credible limits to the accuracy of reported value. So we report any value, so it provides the credible limit to the reported value. And when we want to do the uncertainty analysis, there is a little mathematics is involved. Suppose there is a function y, x1, x2, x3 and xn, right? I will give you an example. For example, we are measuring heat carried away by the cooling water in a condenser. So that is going to be Q is equal to mCp delta T. Now here two things will be measured. One is mass flow rate in kg per second and delta T in degree centigrade. And while doing this measurement, it will incorporate certain error, and this will also, measurement of temperature will also incorporate certain error, in maybe expressed in terms of percentage or absolute terms in degree centigrade, okay, kg per second. Now these two errors will be accumulated. Suppose this has a A1 error and this has, let us say, this has E1 error and this has this one. Delta T has E2 error. So error in Q, shall it be E1 plus E2? It will not. It will not. So in order to find this, when y is a function of, here because mass flow rate is a function of, not mass flow rate, heat transfer. Heat transfer is a function of, heat transfer rate is mass flow rate and delta T. Similarly, we have taken here some y is a function of x1, x2, x3 and going up to xn. Then y plus delta y, right, change in y due to error in the measurement 1, 2, 3 and 4. It has to be estimated, right? We cannot determine this, this has to be estimated. So this is going to be equal to f x1 plus delta x1, x2 plus delta x2 and so on, and it will go up to xn plus delta xn. Their cumulative effect. Now this function can further be modified as f x1, x2, x3 plus delta x1 del f by del x1 plus delta x2 del f by del x2. Right? So this function is partially differentiated with delta x1 multiplied by delta x1, partially differentiated delta x2 multiplied by delta x2 plus half. We can continue with this series, delta x1 square delta square f by delta x1 square plus and so on. But these values will be neglected and they will be rounded off. And now we have y plus delta y. So this y and this y f this will be, they will be cancelled, and we will be getting just a minute. And we will be getting delta y as delta x1 del f by del x1 plus delta x2 del f by del x2 and it will go on up till del xn delta f by del xn. Right. Now the question is, now this is differentiation of with respect to the first parameter, error in first parameter, with respect to second parameter, error in second parameter, and the nth differentiation with partial differentiation with nth parameter. This is only error in measurement, delta x1, delta x2, delta x3. Now this error in measurement we are considering as uncertainty in measurement, right? And then we can have the final expression as uncertainty in the measurement of y is equal to under root uncertainty in the measurement of 1 or x1, then delta f by delta x1 whole square plus uncertainty in the measurement of x2 delta f del x2 whole square plus uncertainty in measurement of x3 del f or f by del x3 whole square and so on up to nth term. Now the question is why we are adding, squaring and adding, or it is known as a Pythagorean sum, why we are not simply adding these values, right? This question may arise, and for this purpose, first of all, the purpose of this is that any plus minus contribution is not accidentally cancelled. Any contribution in the uncertainty by the virtue of being x1 delta x1 positive or negative, they are not accidentally cancelled. Suppose this is negative error, this is positive error, this is delta x2 is positive, this delta x1 negative. This should not be, in fact, module of these has to be added. Module of delta x1 plus module of delta x2 like this. So in order to ensure that accidentally it is not done, square has been taken. Now second thing is, in this case, large source of error is magnified. Large source of error is magnified, reason being, for example, error in the measurement is, let us say there are two measurements x1 and x2. x1 the measurement error is 12%, x2 measurement error is 5%, right? So now here if we take the Pythagorean sum, you will know that the final error will be 13%, not the 17%. That is another reason for taking, because this is the worst case scenario. This will rarely happen, right? So this, when we take the Pythagorean sum, all these issues are addressed. So we never operate, in this case, we never operate in extreme worst case scenario. This is the extreme worst case scenario, right? So for this reason, the Pythagorean sum of all the errors all the uncertainty in the measurement is taken. And suppose now we will take certain cases. For example, there is a case of addition. Now R, there is some function R is a1 x1 plus a2 x2 plus an xn, right? Or it is sum of ai xi I is equal to 1 to n. Fine. Now del r by del xi, so or is equal to ai. For any, if I differentiate with the x1, this will a1, x2, a2, xn, an. So uncertainty in the measurement of r is going to be the sum of ai u xi whole square raised to power 1 by 2 I is equal to 1 to, sorry, here. I is equal to 1 to I is equal to n. Fine. For example, I will give you an example. Suppose we are measuring the temperature with the help of thermocouples, and again the temperature or the heat carried away by the cooling water in a condenser, right? Inlet temperature is T1, outlet temperature is T2. Fine. Now Q is definitely heat transfer rate is mass flow rate Cp T2 minus T1. Now error in the measurement of Q or error in the measurement of delta T, in the measurement of delta T. So delta T is T1 minus T2. So uncertainty in the measurement of delta T is going to be as per this. Suppose error in measurement, this is 0.1 and this is also 0.1. So 0.1 degree centigrade error in the measurement of Ti, and T2 also it is 1 degree centigrade. A1, Ai is 1 in this case. Ai is 1. So we can take 0.1 whole square plus 0.1 whole square raised to power 1.2. So when we take 0.1 square, then it becomes the uncertainty in delta T. Uncertainty in delta T is equal to under root of 0.01 plus 0.01. Now if we take under root of 0.02, it becomes 0.141 degree centigrade. Right. So temperature difference, individual measurement is 0.1 and 0.1, right? So it is not 0.2, it is 0.141 degree centigrade in uncertainty in measurement of delta T. On the other side, inlet temperature is measured by two thermocouples, for example. Inlet temperature is measured by two thermocouples. So each thermocouple has accuracy of 0.1 degree centigrade. So T1 is TA plus TB, which are fixed at the inlet divided by 2. So uncertainty in the measurement of T1 is going to be equal to half, A1 is half, and uncertainty is 0.1 square plus again half 0.1 square. Fine. And then we get now we get 0.01 divided by 4 plus 0.01 divided by 4 raised to power 1 by 2. Or we can say it is half of 0.02 raised to power 1 by 2, or it is 0.0705 or so. So you can see when we are putting two thermocouples, we have improved the uncertainty in the measurement. Likewise, we can have bunch of thermocouples if we take the average value. The uncertainty in the measurement or accuracy of the measurement shall improve. Now, after this, we will take up a case where we have R as product of different parameters. R is a product of different parameters. So, that is x1 raised to power a1, x2 raised to power a2, x3 raised to power a3, xn a to power n. So, these are the cases. For example, Reynolds number, those who are mechanical, they very well know some constant. For example, flow in a pipe, 0.023, Reynolds number m, Prandtl number n. This is 0.8 and this is 1 by 3. So, such type of relations we have in mechanical engineering. So, R is again del R over del xi, because xi here, xi, okay, is equal to x1 a1 multiplied by x2 a2, and when we differentiate xi, or this we can take xi, xn, okay, and when we take xi and a to power I, right, it becomes ai xi a minus 1, and then we go up to xn, right, or we can write this as R by xi and this is ai. This can be always be written as ai, because this if you numerator and denominator if you multiply by xi, then again you will be getting this expression. Likewise, you can do for n number of values, and ultimately you will find that this R can come down here. So, del R by R is equal to ai del xi by xi, right? And when we say the uncertainty in the measurement, it can be expressed in terms of percentage because it is del R by R. It can be expressed as sigma ai u xi, this is uncertainty in xi, divided by xi, I is equal to 1 to n raised to power 1 by 2, right. So, this is how the uncertainty, this will be in the terms of percentage. If you want to have extra value, so an absolute value, then it has to be multiplied by R, right. So, both the cases we have discussed. Now, we will go for certain numericals, because solved examples will give you the insight of the things. Let us start with the solved example number 1. Now, in solved example number 1, it states the resistance of a certain size of copper wire is given as R is equal to RO1 plus alpha T minus 25. R is equal to RO1 plus alpha T minus 25. This is the variation of resistance with temperature. Okay, where RO is 15 ohm plus RO is 15 ohms plus 0.4 degrees centigrade, plus minus 4 degrees centigrade at 25 degrees centigrade, right? Alpha is equal to 0.005 plus minus 1%. It is in terms of percentage, right? Temperature coefficient of resistance, the temperature of wire is T, again 100 plus minus 1 degree centigrade, right? Calculate the resistance of the wire and its uncertainty. So, resistance of the wire at 100 degrees centigrade. So, it is very simple. R is equal to RO is 15, 1 plus 0.005, T minus, T is 25, sorry, T is 100, 100 minus 25, and this will give the final resistance, and it is going to be 0.005 into 20.625. So it is 20.625 ohms. Now we have to find the uncertainty in the measurement. So we'll differentiate R with respect to RO, R with respect to alpha, R with respect to T, right? So del R by del RO is equal to 1 plus alpha T minus 25, right? So is equal to 1 plus 0.005 into T minus 25 is 75, and that will turn out to be 1.375. Let us confirm this. 75 into 0.005 plus 1, 1.375. Okay. Now del R alpha. When we are differentiating this with alpha, we will be getting only RO T minus 25. So RO is how much? 20.625 into 75. So we will be getting 15 into, this is T minus 25 is 75. So 15 into 75, it is going to be equal to 1125. 15 into 75, 1125. Okay. Now del R by del T with respect to temperature. Now when we are doing it with respect to temperature, it is only RO alpha, right? And that is going to be equal to 15 into 0.005, and that is equal to 0.075. Sorry, not 0.075. Okay, so now we have partial differentiation of R with respect to RO, alpha and T. Now using this information, let us note them somewhere that del R by del RO is equal to 1.375. Del R by del alpha is equal to 1125, and unit we can write ohm, and alpha is degree centigrade, and this is going to be unitless. Delta R by del T is equal to 0.005 0.075 ohm per degree centigrade. Huh? Now, uncertainty in the determination of R, not measurement of R, in the determination of R is uncertainty in the determination of R is partial differentiation R with RO, right, and error in the measurement of RO. So, partial differentiation is 1.375. Error in the measurement of RO is 0.4% of 15. 0.4, this is percent, not degree centigrade. 0.4%. So, it is going to be 0.06. 0.4%. We will square this plus again next term alpha, it is 1125 multiplied by uncertainty in this. So, 5 into 10 to power minus 3, 5 into 10 to power minus 5. So, it is going to be 5 into 10 to power minus 5 whole square plus temperature. So, uncertainty in temperature 0.075. So, this partial derivative of temperature is 0.075 and uncertainty in the measurement is 1 degree centigrade, right. So, it is 1 and square is taken and we will take under root of entire expression. So, this is going to be like this. Now, this value is 6.806 into 10 to power minus 3 plus 3.164 into 10 to power minus 3 plus 5.625 into 10 to power minus 3 raised to power 1 by 2, right. And here if you see that highest contribution in uncertainty is coming from here, and this is delta R by delta RO, right. And if we further resolve this, and it is going to be 15.595 into 10 to power minus 3 raised to power 1 by 2, and it is 0.125 ohms. This is the estimated uncertainty in the data, because we are not doing any measurement of R. So, uncertainty in the determination of R is 0.125 ohm. If you want to express in terms of percentage, you simply divide this simply divide this 0.125 divided by this 20.625 multiplied by 100. This will give you uncertainty in the measurement in terms of uncertainty in the determination of R in terms of percentage. So, this is one example regarding determination of uncertainty in the measurement. Another example is if two resistors R1 and R2, they are connected in series. So, I will rub this off. There are two resistors R1 and R2. They are connected in series. It means this is R1 and this is R2, right? And voltage drop across each resistor is measured as R1. Voltage drop across the R1 is, so E R1 is 100 volts and plus minus 1 volt. And voltage across R2 is 15 volts plus minus 0.05 volts. Right. So voltage we have measured with 1 voltmeter here, 1 voltmeter here. This voltmeter is showing 100 volts. This is showing 15 volts with some error in the measurement. Now the R2 value is given. R2 value is 0.075 ohms plus minus 0.25 percentage. This is the percentage of measured value. It is always, if it is written like this, it is always measured. So dissipate, find out, determine the power dissipated in R1, how much power is dissipated in R1, and uncertainty in the determination of the power. Mathematically, it is very simple because once R2 is given, a voltage is given, we can always measure the current. And current is going to be same in both the cases. So current is E R2 divided by R2. And once we know the current, well, then we can always measure power in dissipated in resistor 1, that is IR. So I is E R2 by R2. This is current multiplied by the voltage will give the power. P is equal to VI. So that is E R1. Now we have power as a function of R2. This is a voltage in R2, voltage in R1, and resistance R2. So power is calculated 100 into 15 by product of the voltage divided by 0.075, and it is going to be 20,000 or 20 kilowatt. Let me check. Okay. Now uncertainty in the measurement of power. So uncertainty in the measurement of power, because now this is a case of products, right? So uncertainty shall be calculated as uncertainty in power divided by power is equal to A E1, uncertainty in measurement of E1 divided by E1 whole square, plus A E2, uncertainty in E2 divided by E2 whole square, plus A R1, sorry R2, A R2, uncertainty in R2 divided by R2 whole square raised to power 1 by 2. Now here this values are 1 because we have this AE1 is 1, A2 is 1, and this is minus 1, right? So here we will calculate uncertainty in power divided by power is equal to 1 into error is 1 by 100 whole square, plus again AE2 is also 1, so 1 into 0.05 by 15, plus here it is minus 1, right? And then it is 0.0 into 0.0025. It is given in the terms of percentage. So, because it is given in the terms of percentage, right? So, this is the mathematical expression for delta U. So, here we get, if we solve this, we will get del UP by P as 0.025 0.0108, or error in the measurement of uncertainty in the measurement of power is 216 watt. When we multiply this by 20,000, right, then we get 0.0108 multiplied by 20, 216 watts. So this is the uncertainty in the measurement of power. It is 216 watt, or if you want to express it in terms of percentage, it is 1.08% of the measured value. Right? This is all for today. Thank you.